All right, let me try another video solution. How about number 39 here? So 39 says we have a vertical cylinder with a cross-sectional area A and is filled with a tight fitting frictionless piston of mass capital M as shown. So it looks something like this. Maybe this is the cylinder wall. Maybe here is the bottom, and then the piston itself is in here, kind of the handle going up, maybe even something you could push on. But in here then is this set of gas molecules. Okay. A says, if N moles of an ideal gas are in the cylinder at a temperature T, so N and T, so it sounds like symbols here. What is the height H? So they got a little picture here of H. What is the height H at which the piston is in equilibrium with its own weight? Okay, so what they meant by the piston at equilibrium really goes back to Physics 121, and you would say the sum of the forces in the vertical direction come out to be 0. So what's pushing up is the pressure in this gas. So let me say pressure in the gas times this cross-sectional area. That's what's pushing up. Now, what is pushing down? Well, what's pushing down is the weight, mg, of this piston, but also, easy to overlook, don't forget that there are air molecules here pushing down. So there would be what I would say atmospheric pressure times cross-sectional area A, and that has to equals to 0. By the way, maybe I should have pointed out I'm using force is equal to pressure times area, or pressure is force over area. All right, so this is the upward force coming from the gases that are in here, and then we've got two downward forces, one from the weight of the object itself, but the other one is from the molecules of the atmosphere that are pushing down here, okay? Now, here is where, of course, we're trying to solve for this H here. And so I guess I could rearrange this as PA equals, and I've got this mg plus atmospheric pressure times area. Maybe I'll just divide everything by area, see where that gets me. So I have pressure equals mg over area plus atmospheric pressure. Now, the pressure in this gas container using the ideal gas law, let me put it up here. Remember, PV equals to nRT. So the pressure in the container would be nRT over the volume of the container. And the volume of the container would be the cross-sectional area A of this cylinder, then times the height. Now, if I tried to get H by itself, I might multiply through first by, let me say this right, by area A. So this would be mg, and this would be plus atmospheric pressure times A. Then I would take the reciprocal of both sides. So this would be H equals to nRT, and then this would be 1 over mg plus atmospheric pressure times cross-sectional area A. And then finally moving it to the other side, H would be nRT over mg plus atmospheric pressure times area. And there's really nothing more we can do other than have some symbols here. Oh, and maybe I should have done sub O, because that's what your author does for atmospheric pressure instead of this A. Okay, but other than that symbolism, I'm going to say this then would be the answer, because I have it in terms of what they gave me, the temperature and the number of moles, and just a constant. And other constants like G, and then they gave me the mass of the piston, and atmospheric pressure and cross-sectional area A. Now that's probably the meat of the problem, because the next part of this, I think, just gave us some numbers to work with. It says, okay, so what if you have these values? All right, so what is HF? And so they say the number of moles is 0.2 moles, okay? Now remember, R is 8.31 joules per mole and temperature Kelvin. The temperature they give is 400 Kelvin, so 400 Kelvin. And of course, what's nice about that on the top, moles will cancel off and Kelvin will cancel off, and we're just going to have joules on the top. The mass is 20 kilograms. Oh, this is a pretty significant size piston. Times 9.8 meters per second squared. And the atmospheric pressure varies a little bit, but I think they want us to do the 101,300 pascals, which is a Newton per square meter. And then they give the cross-sectional area as 0.00800 meters squared. And maybe I'll start with the units here. You can see that kilograms times meters per second squared is a Newton. And then, of course, meters squared would cancel in Newton, so you'd have newtons added together. So in the top, you would have a joule, and in the bottom, you would have a Newton. And if you remember, a joule is a Newton times a meter, so when you divide it by a Newton, you're left with units of meters, as we should, since we are asked for, what is the height. So our unit analysis works good here. Let me punch in the numbers here. Okay, so in the bottom, I have 20 times 9.8, and I'm going to add to that 101,300 times 0.008. So there's the bottom. Now on the top, I have 0.2 times 8.31 times 400. So then if I divide that by the last answer, I get 0.661 meters, or 66.1 centimeters, for how much the height is here. All right. Take care.